Okay, so we're going to finish up discussing the imaging analysis of holographic optical elements today. And so we have our midterm also coming up on this is the 22nd of October. I think I kept saying the 24th, but the 24th is a Saturday. So this is a Thursday. And there will be 3 or 4 problems. I will, I'll tell you what, maybe today or tomorrow I'll post the last year's midterm so you can start getting an idea what to expect on the midterm. And then on the 20th, the lecture beforehand, I will go over last year's midterm and show you how to solve those types of problems in relatively short order. So you'll be well prepared for that. I think I might have mentioned that there's only this last homework set would be the last one, but I think there is actually one more on a short section on coherence, and I think there's maybe 2 or 3 problems there for you to work on. That assignment will most likely, that'll be due on the 20th, and again, I can post the solutions for that. I think Thiago said he has solutions for homework 2 that are now posted on D2L. Have anybody looked at those? Or?
I just saw that it was.
Okay. Yeah, he was a little worried that it wasn't there yet because he didn't get a notice from the D2L, group or whatever. Okay, good. So, all right. So what we're going to do today is to look at these third order aberration issues. And so, up till now we looked at various ways of doing the paraxial imaging, and just like you have in other types of optical design analysis, we need those paraxial image points in order to provide a basis for figuring out the higher order terms in the phase functions that describe those fields. All right, so we have again. So we talked about like for the real image, and by and large, for the aberration analysis, we'll be looking at the real. Well, I'm calling it real analysis, but this refers to the secondary image that we discussed in the sense that we had X4, Y4, and Z4 for the coordinates of the paraxial image. And so again, so what we're looking at, and again, so for that U4, that was equal to the phase of P, O star, and R, giving us this kind of conjugate or kind of converging field rather than a diverging field. And that had a phase which was, again, phi P minus phi O plus phi R, corresponding to those field products. And so the way, there's a couple ways of looking at this. So first off is that if we have our hologram and we're, say, reconstructing it in such a way that a paraxial image is formed. So we have some image point up here, x, xi, yi, zi, and again, this would, maybe if this were a real image, again, this might correspond to x4, y4, z4 here. So again, so we would have a wave that is converging to that point, giving us that paraxial image. And so what we'll be concerned with now are differences from that paraxial image. So we may have some other function that more accurately describes the true phase for that reconstructed image field, looking something like that. All right. So really, what we're looking at, or will be looking at, are kind of the differences, or the phase difference between the paraxial and the next stage or next set of terms in the phase description, and these we'll term these as the third order terms. But as we'll actually see, they're third order in ray terms, but they're actually fourth order in wave. Okay, because in order to get the ray direction, we take the derivative of the phase front. As actually we'll see later, we'll derive a different way of doing some ray tracing in a bit. So, it's a little confusing, I guess, the first time you see it, but the so-called third order aberration terms are referring to the ray direction, which again is a direction that's, say, perpendicular to this phase front that we have here. So this again is like the direction of the pointing vector coming off that phase. And so this is a derivative. You take the derivative of that phase, get the gradient, and that gives the direction of that ray. Okay, so the derivative, of course, you're reducing the linear value by one order, and so you end up with third order for the ray. Okay, so that's where that comes from. So as I mentioned too last time, so all of this is kind of derived from looking at these the phase functions. Remember, we had our phase function phi that looked like something like a so we had here for the complete phase, we had say exponential here of, so this is say a sub r or something like that. And so here we had a phase function which was what am I doing here? Okay, sorry about that. So we have the phase, all right. So the phase was, say for 3 or for 4, was equal to a pi over lambda 2 times x squared plus y squared, that factor times a 1 over, say, zp plus mu over zo minus mu over zr. And then we had a minus 2x xp over zp plus mu xo over zo minus mu xr over zr, and a minus 2y yp over zp plus mu y0 over z0 minus mu yr over zr. Okay, so this, by the way, this was, again, just the first order, and so that all came about from reducing this radical that we had with these square terms, where we had, say 1 plus b, where this b is equal to x squared plus y squared over z. And so this we wrote as a 1 plus 1/2 b, and there could be an expansion here. So this term that we have here is actually corresponding to this. The next term in this set is minus 1/8 b squared for the binomial expansion, and then there's also other terms as well. But if we now just look at that term has the form that we want for describing the third order terms. All right, so the phase for the third order are going to look something like 2 pi over lambda 2, and then we have that 1/8 factor, minus 1/8, so we have minus 1/8 times, lost the z4 cubed down there. And then we have x fourth, so this is where the fourth order terms come in, as I mentioned, for this phase. x4 plus y4 squared, I'm sorry, x4 plus y to the fourth power plus 2x squared, y squared minus 4x cubed, x4. And I won't write all these out. They go on. There's a whole bunch of terms here. The important point is, again, these are fourth order terms in this part of the expansion. And those are the ones that will deal with for the third order aberrations analysis. All right. So, so the next step in this is to, and this is often done in other, kind of ray tracing analysis and so forth, and that is to go from the rectangular coordinates to circular or polar coordinates. And so here, the reasoning for that is that most lenses are circular, and most apertures are that we deal with in optics are circular. So we can have a distance away from the origin and an angle theta. Here's x and y, and so we have that this theta now is, theta is equal to the arctan of y over x, and the distance that we have here, rho, is equal to x squared plus y squared to the 1/2. All right. So if we put things in the circular coordinates, we can then rewrite this fourth or third order aberration term here that we have in the following way. So we can write this portion of that phase as w, and that's equal to 2 pi over lambda 2 times minus 1/8 rho, the circular coordinate distance from the origin, rho to the fourth power, times an aberration coefficient, s, and then we have plus 1/2 rho cubed times c sub x cosine theta plus c sub y sine theta. So we can have kind of different, a different form of the coefficient in the two orthogonal directions that we have. Minus, the next term is minus 1/2 rho squared a sub x cosine squared theta plus a sub y sine squared theta. And then there could be a cross term, a x y. Sorry, there's a 2 in there. Cosine of theta, sine of theta. Okay, and then there's another term related to this one, minus 1/4 rho squared f, and then plus one. The last term is 1/2 rho times d sub x cosine theta plus d sub y sine theta. All right, so this again is the, this is really representing this phase difference with the paraxial phase, right, as we mentioned here in this this diagram that we have here. This is really looking at what's happening between these two phase descriptions that came out of that binomial expansion. Okay, so as you know, most of you, well, I would say a lot of you realize, so this S is this is a coefficient, so it's not, you know, not a variable. So that's our corresponding to spherical aberration. The C values that we have represent coma. A represent astigmatism. F is the field curvature. And D is distortion. So again, as described in that paper by Meyer that I posted on the website, we can categorize this phase difference that we have in terms of things that are fairly well known from other optical design problems that are encountered. So this has advantages in a couple of different ways, because now we have something which is kind of bridging with more conventional refractive and reflective optical design and analysis. And so we can compensate for these aberrations in hybrid systems where we would use, say, lenses in combination with holographic elements. There's very different properties in corrective features using holograms as opposed to lenses. But again, you can use this in order to compensate for aberrations in different hybrid systems. And these have been used quite a lot over the years. Okay, so let's look at some of these different aberration coefficients briefly to get a sense of what we could do with them. So here, if we look at the spherical coefficient, that we can describe as, again, these are all based on constants that we have. So the spherical aberration, S3, for the primary image is 1 over ZP cubed plus mu, again, where mu is equal to lambda 2 over lambda 1, mu over Z0 cubed minus mu over ZR cubed minus 1 over Z3 cubed. Okay, so again, the important thing to notice here is that they only contain the axial positions of the point sources used in construction and reconstruction. So they are, in fact, it is in fact a constant. It's a coefficient. It's not a variable. All right. And again, it shows kind of, you can see very explicitly here that it's a residual difference between the holographic reconstruction and the paraxial image point. And this paraxial image point that we have, Z3, for instance, was ZP, ZO, ZR over ZO, ZR plus mu ZP, ZR minus mu ZP, ZO, if you recall from the paraxial image locations that we have. So we have that for the, again, so this is for the primary image. There's a different aberration, spherical aberration coefficient for the secondary. Remember, those two images that we're going to form, they depend very much on P, this reconstruction point source that we have. So if we're using the original point source or something close to it, most likely the primary image is going to form with a very good definition or fidelity. If we reconstruct with the conjugate beam or conjugate point source, then the secondary image is going to form an image. And that, in that case, that one could have a much better image quality than this one. So there's actually two different aberration coefficients for the primary and secondary image. So for the secondary image, S4, this is equal to 1 over ZP cubed. There's a change in sign here, minus mu over ZO cubed plus mu over ZR cubed. But we still have a minus 1 over Z4 cubed. Again, because these are, again, representing this difference between these two ways of determining the image point. Okay. Now, there's a couple of situations that we can get from looking at these aberration coefficients. We can come up with a couple of different situations where we can minimize the aberrations. Now, one thing here is to notice that the spherical aberration, just as in other systems, only is depending on the kind of the axial distance away from the origin. It doesn't depend on the angle, where in the aperture we're coming from. And so, because of that, if we have a situation where ZR and, say, ZP are at plus or minus infinity, so we have plane waves for both the construction and reconstruction fields, then we end up with a spherical aberration coefficient, which is essentially mu times mu squared minus 1 times 1 over ZO cubed. And in this case, when we have these plane waves, the spherical aberration can be eliminated if lambda 1 equals lambda 2. So in that case, we have S equals 0, because that sets that term equal to 0. Okay? So there are some situations where we can actually eliminate some of these aberration terms. And there's some techniques later that I'll show one technique later where we can balance some of these aberrations to get better overall performance of a particular system. Okay? So let's look at some of the other coefficients quickly here. So we have coma. And coma now is going to depend on, it also depends on not only on Z, the axial value that we have, but it also depends on the coordinate in the axis, all right, or in the aperture of the system. So here we have C sub x3. I'll only give the x versions here. The y's are similar. C sub x3 is equal to xp over zp cubed plus mu x0 over zo cubed minus mu xr over zr cubed minus x3 over z3 cubed. So again, we have this difference between the construction and reconstruction coordinates and the paraxial image location. And similarly, we'll have a different version for the secondary image, x4. So here we have xp over zp cubed minus mu xo over zo cubed plus mu xr over zr cubed, again minus x4 over z4 cubed. Okay. So in this case, we can kind of minimize the coma if we have these two terms here being equal to one another or equal and opposite to one another. Well, in the 3-dimension, if we have these two being equal to each other, we can kind of minimize the effect of coma in the system. So again, there's a balancing that could be done in order to kind of reduce the overall effect of the aberration coefficient. For astigmatism, these are going to be functionally, so notice here the coma is dependent on like an x over z cubed, all right, kind of dependence. The spherical is on 1 over z cubed. Astigmatism is x squared over z cubed, as is the field curvature. And I won't write all of these out there in the notes, but the functional form here, say for AX3, is equal to xp squared over zp cubed plus mu xo squared over zo cubed minus mu xr squared over zr squared, and again minus x cubed squared over z3 cubed. Okay. So, and again, so the other terms are similar, as are the F terms. Also have this kind of functional dependence, except the field curvature is more a function of the x and y are kind of coupled to one another, and so in that case, the well, let me write it out here. F3 is equal to xp squared plus yp squared over zp cubed. So it still has this lateral dimension squared divided by the axial dimension cubed, but it incorporates the y in it as well. And so we have to insert that into each of our terms. So we have mu xo squared plus yo squared over zo cubed minus mu xr squared plus yr squared over cr cubed. And as we're doing up here, this is then minus x4 squared plus y4, I'm sorry, x3 squared, y3 squared. We're using the 3 value, or the primary, over z3 cubed. Okay, so the field curvature differs a little bit in the sense that these values are actually coupled, you know, and in case of the astigmatism, they're treated separately. Okay. All right, and then the final aberration that we have is distortion. And you know, this looks very similar to, by the way, so the coma has kind of a comet tail kind of thing where you usually have a high intensity here, and then this kind of decreases in intensity. Spherical is just kind of a symmetrical blur that you have. Again, it's sort of like, you know, if you have a focal shift in a lens, you know, the beam comes down, and so basically if you're looking at it here instead of at that point, so it has a larger spot diameter. Coma has that functional form. Astigmatism has kind of a different imaging in radial and axial, or radial and circular dimensions. And distortion has a kind of a flattening and broadening. If we look at a image which is affected by distortion, if it were supposed to be a square or a rectangle, we could have what's called, this could collapse a bit here, forming what's called pincushion distortion. Or it could expand a bit like that and form a barrel. So it could either kind of explode or implode, depending on the sign and nature of it. And so we have here dx3, for instance, has the functional form of xp3 plus xp yp squared over zp cubed. So here again, so this one has a cubed in the lateral dimension in the numerator and a cubed in the axial dimension in the denominator. And the other terms are kind of similar to what we had here, except it has this as the numerator for all of them. So I'll just quickly write out one of these. So we have mu xo cubed plus xo yo squared, kind of similar to that, over zo cubed, and then we have one term like that. So we have minus mu xr cubed plus xr yr squared over zr cubed, and then we have minus x, I don't know why, in my notes are wrong. I should correct these. X3 cubed minus x3 y3 squared, and in my notes these are 4s, they should not be that. Z3 cubed. All right, so again, very similar, taking the points used in the construction and reconstruction and subtracting out the paraxial. Yes?
How do we define the x and the y direction such that we know which one gets the cubic term and which one gets the squared term?
Well, again, so we would define those with the, again, if we were using this angle, the angle could actually help us in defining, when theta is equal to 0, we would have x, and 90 degrees, we would have y. So that would be the way in which you'd be able to do that.
But the angle is just arbitrarily defined, isn't it?
Well, no, it's defined relative to the x-axis. So, and we have, wherever my, so you see here we have, and we have also a cosine and sine here, so these are 90 degrees out of phase in their definition, okay? So it's, it's a little, it's a little tedious, all these aberration coefficients. I just wanted to show you where they come from, and most of the time I usually do a array analysis, although in one example that I'll maybe get to later is using constructing a hologram in one wavelength and reconstructing it in another wavelength, you're going to end up with aberrations. And so by kind of forming intermediate holograms that encode these different aberrations, you can actually eliminate most of the aberration that occurs from that wavelength difference between the recording and reconstruction. So knowledge of the aberration coefficients helps you. It's mainly intuitive, I think, or can help in other ways too, but it provides a good intuitive way of understanding, first of all, what your system is suffering from, and then maybe give you some insight on how to correct it. So let me give an example of, maybe that'll help. So earlier when we were just calculating the paraxial image locations, we had this problem, right? So here we have x and y and z, and we said that we had an object point out here at 1, 0, and minus 5, and we used a reference beam that was at 11 degrees with a plane wave from infinity, and then we had so here's r, and then we had p here, so we have theta p equals 10 degrees. Okay, so before we just calculated where the paraxial image points were for that particular reconstruction condition, but now we can actually calculate what the aberration coefficients are going to be for that system. And so here, so we have these points and we have these at infinity. We also said that lambda 1 was equal to lambda 2. All right, so that again sets mu, that ratio lambda 2 to lambda 1 equal to 1. And we can then, what we did was, so we have x 0 equals 1 and z0 equals minus 5. We have xr, plane wave, so we're going to set that to infinity in the negative z direction. So we have minus 10,000 and, I'm sorry, zr. And corresponding xr then for that angle of 11 degrees gives us zr tan theta r equals minus 1943.8. And then for zp, we also have plane wave from minus z, so minus 10,000. And xp is equal to minus 1763.27. Okay, and then, so we put those into our calculations for the paraxial image location. So we found for the primary image, here we have x3 was equal to 1.09027, and z3 turned out to be exactly, well, at least to whatever accuracy we're taking it, a couple, 4 or 5 precision accuracy, we still get 5. And then for the secondary, we had x4 was equal to 1.091356, so a little bit larger difference than 1, and a z4 was plus 5.005. Okay, so let's go ahead and calculate the aberration coefficients. Now, an important thing to note here is we have a point source that's kind of off axis here, all right? So we're going to do this, and then we'll do another problem that's kind of related and see how we can reduce some of the aberrations by having the geometry set in a certain way. So one thing to note here is that since we have two plane waves, the reference and reconstruction point at infinity, and we have the same wavelengths, we know that our spherical aberration is 0, right? Because that's mu squared minus 1 over CO cubed, all right? Because that term is 0. All right, but what about the other aberrations? So let's look at coma. We'll just look at a couple here. So we have coma. In this case, we have minus mu. Could write this as minus mu times xp over zp mu plus xo over zo mu squared minus 1 minus xr over zr mu squared. That over zo squared. And this comes out to be a value of 7.221, I don't know how many places we need to go, times 10 to the minus 4th, okay? And similarly for the astigmatism, here I end up getting a value that is minus 1.50945 times 10 to the minus 3. So these are, these are pretty sizable aberration coefficients actually. And so the I ended up I did a kind of a ray trace, my own program here of that. And so so I ended up getting something that's, a lot of coma, okay, pretty significant coma factor in there, and a fairly large spot. All right, so so that was again formed with the point source for the object off axis. All right, so now let's do the problem again, but let's put the point source on the axis. All right, so so let's hear case 2. So now we have the point source is on the axis, z equals -5 out there, and we're going to use the same kind of reference and reconstruction beam angle. So we have a beam here of 11 degrees for theta r. I'm sorry, I think that's 10. Let's see, what we're using. 11 degrees for theta r. And so that's that. And we have 10 degrees, a little bit less, for theta p. All right. And yeah, so the other thing I didn't mention too, I'm considering an aperture of 1 in the units like whatever we're using for the Z0 units out there. All right, so now if we do the calculations for, somewhere I have it. Yeah, so now if we do the calculations for coma and astigmatism, I end up with the C sub x. C sub x works out to be, that's not it. Oh, okay, let's see. I think I lost my values that I had here. Okay, no, all right, I'm sorry. Too many notes here. All right, so C sub x is similar. So we have minus 7 point, well, it's similar, but in magnitude, times 10 to the minus 4. But the astigmatism that I end up with, A sub x, is 6.525 times 10 to the minus 5. All right, so 2 orders of magnitude. This was the predominant aberration coefficient that we had. So we can get a pretty significant drop in the astigmatism by putting that object point source on the axis, okay? So, like for instance, in the lab, I had you arrange it this way rather than having that point source off axis. If you put that point source off axis, you're opening yourself up to other aberrations. And here, so here's kind of the situation or the resulting ray trace. So you can see here, this overall distance that I have here is about 0.03, whereas this distance here is about 0.008, the difference between these values here and there. So again, a pretty significant drop, more than about an order of magnitude almost, a drop in that difference. Okay, so again, so looking at the aberration coefficients can be very useful in figuring out how to reduce the overall, or how to improve the overall image quality of the holographic images. All right, so the next thing let's talk a little bit about are evaluating holographic images using simulation programs, optical simulation, optical design, or simulation programs. And so probably the most popular are Zemax and Synopsys. Formerly, I guess, known as Code 5. I don't know if it's still called Code 5 or not, but anyhow, Synopsys, I guess, took over AR Associates, and they're called Synopsys. So anyway, I don't use that program anyway. It's too expensive, so I use Zemax. And Zemax is very handy and really a really good tool for optical design. And there's several different ways that you can, if you have Zemax, I think all students in OpSci at least have Zemax available, and we have it in my lab. If you wanted to play around with that a little bit, you're welcome to do it. So Zemax allows you to evaluate holograms in 3 different ways. Now, I think Synopsys now has a kind of a routine on it, so you can do both the ray analysis and a diffraction efficiency calculation. Zemax doesn't have that yet. I don't know if they're going to come out with that in the future, but nonetheless, you can do the ray analysis, and then there's some simple ways of implementing or augmenting with the DLL, the coupled wave analysis that we're going to go through later in the class or in the course. And so you can implement that and do an analysis of the efficiency of the hologram as well. So so at any rate, in Zemax, there's 3 different ways to evaluate a performance of a holographic element. And these are in the surface types in the main editor that you have. So one of the surface types is called hologram 1. Okay, and hologram 1 is, so hologram 1, then there's a hologram 2. Hologram 1 has both the construction beams, or both construction beams, are point sources. Okay, and they're either point sources that are either converging or diverging. All right. So both. Okay. So I guess the important thing here is that both are either converging or both are either diverging. All right. The hologram 2, if you wanted to use that, that would be the case where one beam, say the object beam, is converging or diverging, and the reference beam is diverging or converging. So one is one and the other is the other form of the shape of the phase front. All right, and then the another form of surface type that you can use is called the optically fabricated hologram. All right, and so this allows you to treat non-point sources to form the hologram. And this would be, for instance, you can use a computer-generated hologram in order to generate the field that you want for that system. So in a computer-generated hologram, again, I mentioned this, I think, briefly earlier in the course. You use a kind of a mathematical code to write a pattern that you can then form by lithography in a surface, and then when you illuminate that device, you end up with an arbitrary wavefront. Could be an aspheric wavefront that you might need for a particular application. So in this version would be one in which you'd want to use this optically fabricated hologram surface type in the description. Okay, so with that, I mean, you can then, once you do that, you can look at, you can do your layout. So you have a system that shows here some chromatic effects. So the colors, I don't have the colors here, but these are different wavelengths here, and so you can see that produces a lot of chromatic aberration in that particular lens. And then you can do a spot diagram. These are functions of different field angles. So here's at 0, so you get this nice stigmatic point. And then as soon as you go a little bit, this is only like 1 degree off axis, you start seeing a pretty significant coma. And then here at 2 degrees, you get a lot of coma. And you can also look at sort of the ray fans here, and you also see that there's a lot of aberration here as you go further away. And this is, yeah. So anyway, so you can use a ray trace program to analyze holograms. And again, they're used a lot. Yeah.
What do the arrows on that plot show us?
The arrows?
You have 2 red arrows in the
Oh,
middle of...
yeah, okay. So what I was just showing here is that you have kind of a different height of this ray intercept here relative on the one side versus the other side. So that's showing kind of the effect of coma. If you had this sort of, just this kind of, I guess, if you had this completely parabolic and equal on both sides, that would just be spherical in the system. Okay? Make sense?
Yes.
Okay. Yep. Yeah, I had to look at it for a second there too. Yeah, so, okay. Okay, so let's look at something else now. So I mentioned, if we had this computer-generated hologram, we can create a aspheric wavefront, all right? And so the actual ray trace formalism or formalism that I had given you doesn't really work a whole, really that well when you have kind of arbitrary phases that may sort of exist on arbitrary surfaces. So, for instance, if we have a kind of an arbitrary wavefront here, how can we, model the various ray trajectories that we would use and come up with a ray tracing algorithm for analyzing this? All right. So here, if we look at this, right? So here, this is at one point in time. Here's at a later point in time, or we can also think of this as, a wavelength difference apart. So, and we have some arbitrary phase, phi of x, y, z. Well, as I alluded to earlier, if we know what that phase function is, if we take the gradient of that phase function, we'll then get the direction for the ray, or the pointing vector, for instance, going from that surface. So if we have kind of an arbitrary phase front, or like an aspheric phase front, or we want to model some things that are on arbitrary surfaces, we can use direction cosines in this case that are based on this gradient. So we would have, for the x direction cosine, this would be equal to lambda over 2 pi in order to offset that phase phi sub j with respect to x. The mj equals lambda over 2 pi phi, the derivative, partial derivative of phi with respect to y. And the nj is equal to square root of 1 minus lj squared minus mj squared. Okay, so we can come up with this kind of arbitrary description for the ray trace or the direction cosines, again, using the definition of what we mean by the ray, okay, relative to that gradient of the surface. Okay, so this brings up kind of an interesting point. So when we think about the hologram, it really is a kind of a phase transformation operator, right? And let's talk about that for a second. This is quite a useful way of thinking about the hologram. So you can think about it more in terms of a system function rather than just a physical optical element. All right. And so what do we mean by that? Well, again, if we think about what the hologram does, we have some arbitrary incident phase, could be pretty much any form that we have. We then pass it through this operator or filter. So here's our hologram. And then what we can do is whatever we like, right? If we make a recording with a second beam, we end up with an output phase which looks nothing like the input phase. So this hologram is really we can think of that again as a phase transformation operator in which we transform whatever input phase that we have to a prescribed output phase, all right? So again, we could just express that simply as our holographic operator is equal to what we want for this holographic operator. We can say that we have a phi sub out. Again, this is a function of x, y, perhaps z equals 0. And at the hologram plane, minus phi incident, again at x, y, 0. And we need to form that by, again, our construction process, which involves a reference, so we have, and an object field, or an object phase. So we have a object phase minus this reference phase. Okay, so these may be the same as the output in incident, or they may be different. It doesn't matter, right? I mean, we can form them. We can form the hologram operator by controlling these. These can be, again, formed by this computer-generated hologram to form some sort of aspheric surface. And we could end up with if we want to focus light to a point, or if we want to bring light to within a reasonable point that's acceptable for a particular application, we can also do that. So let's look at an example. Okay, that was a little bit abstract, but let's look at a very practical example here. And that is that we want to have a Fourier transform lens that has a acceptable image spot over a certain field of view. Okay, so we have a field of view, a delta alpha, say, field of view, and we need to have a sort of a delta x or delta y, which is our image point, less than some epsilon, all right? Now, as I mentioned, or briefly last time, and so first off, this the Fourier transform hologram that we have is simply the type of hologram we've been talking about all along. So, and these are very practical elements that have been used in some optical signal processing instruments in the past. So here, Fourier transform hologram, we have a plane wave that comes in, and it forms a spot. Okay. Now, normally in the past we talked about, reconstructing this with the same beam, or the same as the reference beam. So we have R equals P, and we get a nice spot here, nicely focused. However, what we want now is we want to have some field of view. So we want to change that, sort of similar to that previous example that we talked about here, where we form it at 11 degrees and reconstruct it at 10 degrees. So here we're going to have some field of view for the reconstruction angle. And we still want to have a spot. So here's, say, epsilon. So we want to have that spot remain less than that epsilon. So that could be, a case where, for instance, if we have a camera, we may have pixels that are, maybe 2 microns in width or in length. And so the spot doesn't really have to be any smaller than that. So we can allow that spot to grow and still get the resolution of the camera, which is fixing the overall system resolution. And so we don't need to have exactly a very, a precise point focus in that system. So let's use that to give us a field of view here, this delta alpha. All right. Okay. So to get that, all right. So what functional operator do we need here for the hologram? So we want to know what is the operator function that we need as we defined it up here. So we want to have this object in reference that'll give us a prescribed output. So the actual form that we want, to some extent, if this were a spherical wave, we would get a point focus down here. But if we kind of relax that, what we need now is a kind of a flatter function, right? A flatter function that'll give us a good point, a reasonable point image there and there. Maybe it starts to deteriorate as we go further off, but we don't need to have that point focus only at the one location. We want to have a little bit bigger spot, but spread over a larger area. That'll give us our field of view. Okay. So the function that we want, this phi sub h hat, is, we're going to say that that's equal to a quadratic phase function, right? Just like our binomial. When we expand that out, we're making an approximation. But what we're actually doing is flattening that spherical wave a little bit. All right, so we have minus 2 pi over lambda, and we have something that looks like x squared plus y squared over f, where, say, this is the focus of that lens element that we have. All right, so that's our hologram function. What is the incident function that we have? Well, phi incident, this is going to be a plane wave that can change angle a little bit. All right, so we're going to have a incident phase, which is 2 pi over lambda, and we could have a little bit of a tilt in the x and a little bit of tilt in y, perhaps. Okay, where again, so alpha is just equal to sine of theta x, and beta equals sine of theta y, or what have you. All right, so we have a little bit of a tilt involved in that. And so what is the function that we want? Remember, we have this phi out now is equal to phi h hat plus the phi incident. And so the function that we want is going to look like, again, an image point over this extended range. And so here we'll have minus 2 pi over lambda times x minus f alpha squared plus y minus f beta squared. Right? This is just a recentered point, so we're going to be able to shift that point up and down a little bit. Because if we're using this in a system, we want to have some field of view. We just don't want it to operate at one particular point, for most applications, at least for imaging applications. And here's our focus. And we could have some other terms here, but this is primarily for our binomial expansion. But this is primarily the function that we would like for that. All right. So how can we actually get this? Well, we can get it by using a computer-generated hologram to generate this quadratic phase function. All right. So here we'll form this hologram in the following way. So we'll use a spherical wave in the object. So we have a focal distance for this spherical wave. So this is going to be the object wave. And that is spherical. Here's the hologram here. And what we're going to do now is encode the quadratic phase in the reference beam. All right. So here we'll draw an axis. Almost came out right. And so we have a lens here, a lens here. We'll put a spatial filter there for a reason I'll explain shortly. And now we're going to use a computer-generated hologram out here to produce this quadratic phase function. And we're going to illuminate this CGH normally, and it will generate the wave off at an angle. All right. So the reason we do that, or in general, is that the computer-generated hologram, for the most part, is not going to be as efficient, say, as a volume hologram. And so you're going to have a pretty large zero order. And so if you reconstruct it in this manner, where the field that you want, again, is your diffracted field out here, that'll allow the zero order to kind of pass through the system and not use that. And then you can match the intensity of this object beam to that diffracted beam for the reference beam and equalize them and get a much higher efficiency hologram here to use in your end product. Okay. And the spatial filter here is, again, just used to clean up the beam, just like it. Oh, I missed the point here. It's just used to clean up that beam a little bit so that you don't get a lot of spurious effects in there, or you may have some scatter in that CGH, and so you can eliminate it just like we do in our lab setups. And then we illuminate the hologram plane with this field. So this now is the reference wave that we have, and it will have in it this quadratic phase function. All right. All right, so the phi sub r that we have, phi sub r for the reference beam, this is equal to 2 pi over lambda times the square root of x squared plus y squared plus fs squared, all right, minus 1 over 2q, or 2fq. So this is for the quadratic, the focus for the quadratic. And we have to do a little bit of something else here. I'll explain in a second. X squared plus y squared, and we're only going to tilt it in the x direction, so we have a minus alpha x there. All right. Now we're going to put in that not only the quadratic in this CGH, but we're going to put a little bit of spherical in there too, because we want to eliminate this wave out of it, and we only want to end up with the spherical wave. I'm sorry, the quadratic phase in this. So because the object field, phi object, this is equal to 2 pi over lambda. It's that function. So we have x squared plus y squared plus fs squared. Okay, so when we take the phi r minus phi o, we're going to end up with just this term here. So we have 2 pi over lambda, 1 over fq, x squared plus y squared minus alpha x. So again, and that's the function that we want. That's our phi h that we want. Okay. All right. So so that's how we can generate and form a kind of a more desirable arbitrary function in the reconstruction of our hologram, and we can use these these generalized ray tracing calculations as well. For instance, now the LR that we had, which was, again, as I mentioned here, if we take the derivative of this phase function with respect to x, here we're going to end up with a x times x squared plus y squared plus fs squared to the minus 1/2 minus x over fq minus alpha. So for instance, we could look at that generalized phase function and come up with our direction cosines very nicely for that, using this gradient of the phase function form for the direction cosines. Okay. Oh, and so, yeah, let me just show you now, too. So using that arbitrary wavefront, this came out of a paper that I referenced here. So here, if we're reconstructing with spherical waves, if we form this and reconstructed it using this spherical wave and the plane wave, we get a nice point focus here at 0, but as soon as we go off that 0 reconstruction angle, we get horrendous aberration here, this large coma being formed. Whereas if we use this process of encoding this quadratic phase function, now we can go off 10 degrees and get 2 orders of magnitude less aberration in that reconstructed point image, or not a point image anymore. As a matter of fact, at the 0 degree here, notice that the spot is larger, but the spot remains small over a fairly large field of view in this case. So it's a very useful approach to making your system perform good enough for the detection process that you're using. Okay, so we'll see you on next week.